Hello, and thanks for stopping by. My name is Stefan Metzger. I serve as science lead for NEON's surface atmosphere exchange observations and data products. And today I'm going to talk to you about exploring natural climate solutions. Could flux towers be useful at industrial scales? Now, why would we choose such a topic? We just returned from the Glasgow Climate Summit, and among others, what's being done there is to consider mitigation actions. Mitigation actions such as figuring out what type of emissions could be reduced in things like factories, power plants, and so forth, but also mitigation actions such as sustainable development, including natural climate solutions that sequester carbon. And all of these things need to be measured, reported, and verified in order to be accountable. Now, all of our countries been coming together and been submitting what's called nationally determined contributions. Here's an example for the United States to reduce greenhouse gas emissions by 50% in the next 10 years. So we were sticking our heads together and thinking, wait a second, carbon emissions, carbon fluxes, sequestration, measuring, hell, that's right down our alley. What can we contribute to actually make this more tractable, make this attractive, and position us well to achieve these goals for the future of our planet? Now, here we go. Carbon sequestration as a principal MRV, measurement, reporting, and verification mitigation action. So this can happen at least in two different realms. On the one hand, we can work through abiotic carbon sequestration, such as pressing liquefied CO2 down into the ground. Or we can work in the biotic realm, biotic carbon sequestration, which is something that we're familiar with in the flux community. So we're going to focus more on that aspect of carbon sequestration here. Now here, let's add one additional dimension. On the left-hand side, we still have our realm of carbon sequestration that we just talked about, so biotic and abiotic. Now what's also coming into play is the supply chain location or jurisdiction where such a carbon sequestration happens. And so within an existing supply chain, so let's say right at the factory or power plant, that is called emission insetting. So we're reducing emissions like right then and there. Now, it's always going to be residual emissions that can then be offset from outside the given supply chain or jurisdiction, and that would then be emission offsetting. And so if we look at that quad chart, we see where we're kind of located with biotic emission offsetting, and we're trying to come up with a tool which we call Emission Observation Data Analysis System, or EODAS, that makes it financially really attractive. And in a sense, it's low tech because it uses nature ecosystems to realize carbon sequestration as compared to some of the higher tech alternatives such as direct air capture, which also makes it initially a bit more expensive. Now let's take a look what we can do if we put all our beans in one bag. So what we see here is a chart where on the y-axis, we see how much incentive is either still required, here positive, or what is already profitable. And in color coding, you see what can be done or realized, kind of different initiatives that can be realized either through biotic, the blue color, abiotic, I apologize, abiotic, the blue color, or biotic carbon sequestration, and different example implementations or combinations thereof. And what we see is that here in the bottom part of the graph, we see a lot of yellow, which shows to us, hey, this is something that could possibly already be very attractive on an economic scale using biotic carbon sequestration, including nature-based climate solutions. At the same time, there are also various combinations of biotic and abiotic that can be very productive and in particular store carbon for a very long duration. Now, this leaves us essentially with a carbon puzzle. If we're saying, okay, we want to quantify carbon sequestration by ecosystem, make them truly accountable for carbon economy, then one thing we know is that no carbon observation method by itself is whole. So they all have different benefits and challenges, principally along two dimensions in terms of how robust they are, in particular when applied to tens to hundreds square kilometer scale, and how accessible they are. And as you can see here, there's several sub-dimensions in terms of accessibility and robustness, and what really plays in there, how financially affordable they are, the type of geographic terrain that they can be utilized over, how inclusive they are, um, on the robustness side, how reproducible they are, whether they are independently validated, and last not least, considerations with regard to additionality and permanence. So essentially what that leaves us with is, wouldn't it be awesome to combine this aspect through something like data fusion? You know, that's exactly what we're setting out to do. And data fusion is nothing new. What is, however, fairly new is to do that in a scale-aware fashion, taking into account the various representations of observations that we have. So for example, we have gridded remote sensing here. Then we have point scale, tree inventories, soil cores, static chambers. And then we, for example, also have a flux tower here, each of them representing very different spatial areas during different temporal periods. And so to actually bring them together in a time space explicit data fusion, that retains a lot more information than what is the status quo in terms of, in particular, machine learning based upscaling. And so what that yields here are essentially half hourly decameter scale accessible and robust project carbon grids on the right hand side. Now let's look at a project where we're actually applying this. So here you see these aotas in action. This is an integrated cattle farm in Wisconsin. And you see here on the left-hand side, if we just look at the flux tower, then essentially we look at a green blob of slime that varies in space and time, essentially also, because we cannot truly attribute at a finer scale where carbon sequestration signals are coming from. Now, when we are done supplementing our flux tower with those additional observations on the ground and in the sky, then a much clearer picture emerges here on the right-hand side. And what one can essentially now do with these half-hourly decameter scale carbon maps, on the one hand, we can perform near real-time problem tracking and resolution. So underperforming project locations here, for example, can be immediately remedied. Overall, it provides project scale, high resolution project scale monitoring in order to optimize both climate benefits as well as economic benefits through time for the landowner. And now here's something beautiful that actually just happened. We are cost effective, which is not something that always happens in academia. So what you see here is a benefit cost plot as a function of flux tower measurement height here on the x-axis, and here on the y-axis the benefit cost. So that's a log-log plot, something to keep in mind. And essentially we see three different areas color-coded in a traffic light scheme. So long as we're down here in the red area, it's not financially attractive yet because our cost outpaces the financial benefit. So there's diminishing incentive to do anything new down here. Now up here, the status quo which is currently principally inventories, either inventories of soil carbon, individual soil cores, or inventories of trees, measuring their circumference. We are right here at around 140% benefit cost ratio. So meaning the project creates 40% more revenue than it costs. So that's financially sound. If we can be better than that, then we're actually increasing incentive not just for adoption, but also for more rapid and more widespread applications of nature-based climate solutions. And now we see here that just the flux tower by itself doesn't quite cut it. Like we don't really get above the status quo. If we, however, combine flux towers with the IOTAs, we are right up there. And we're actually able to increase incentive by likely up to an order of magnitude, because that's the amount that the benefit cost ratio increases. Now, how does this actually then apply to the carbon offsetting process, and how can we incentivize climate action? So what we are proposing here. So let's look at the center here, the carbon economy. At the first slide, we looked at these nationally determined contributions to Glasgow. And right now, there's a lot of incentive bills in the pipeline to realize that on national levels. This aims to incentivize emission reductions right at the factory. There's always going to be residual emissions. And the idea is, through those bills, to make it more attractive to do appliance and voluntary compliance and voluntary carbon offsetting than not, to make that more financially attractive. That creates a market, a demand for carbon trade that we can cater to, for example, through biotic carbon sequestration. Now, the way how this works is a project is being initialized. So there's an inventory being taken of the current baseline sequestration, business as usual. There's being models run, projections. How could we change the land management for additional sequestration? And then once we have those projections, they essentially need to be verified, whether or not they truly happen through time. And that is where we suggest to insert, because that is continuous operation. So that's where the most money is essentially being spent, because that needs to be recurring. If we save order of magnitude costs down here, then that's going to make a transformation to a carbon economy a lot more attractive. In addition, our findings here can routinely feed back to either rebaselines, updates of a current project or new project in similar or different land management realms. Now, this was an example of applying EOLAS for nature-based climate solutions. It is architecturally, however, fairly easy to adopt to other climate-relevant arenas. And one example is such as industry leaks or trace emissions from abiotic carbon capture, storage, and utilization facilities. To summarize, how did we get here and what lies ahead? We only started fairly recently with this. So in January, the AmeriFlux Science Steering Committee created a nature-based climate solutions working group. A half year later only, we already had quite prominent presence at the AmeriFlux annual meeting. So 1 out of 2 days was entirely on this topic. There was also a breakout dedicated to nature-based climate solutions. Now here, we're having several talks at AGU and submitting our first manuscript. There's also in the making EOLAS strengths, weaknesses, opportunities, threats analysis in the coming year. So that's our vision down here. We essentially intend to apply EOLAS to a high density data set, GZ19, and treat that as a mock natural climate solutions project. We then intend to present the results at the Battelle Climate Conference at the Ecological Society of America. Further down the road, 23, hope to equip a neon deployment platform, so essentially a roving tower, with this EOLAS to create a carbon mapper that can be requested and applied pretty much anywhere. And Last not least, in 24, to equip neon eddyflux sites with this kind of capability and hopefully spur some market trials. And so something that we're really looking for right now and being active in our search is to acquire seed funding to accelerate dialogue between academia and industry. So if you're interested in that, feel free to reach out to us. And with that, thank you so much.